Hello and welcome to this video on Neural Processing Units or NPUs for short. Before we dive into the world of NPUs, let's first take a quick look at what a microprocessor CPU is. A microprocessor CPU is the brain of a computer system. It receives input from various devices, processes it and produces output. It is responsible for executing all the instructions that a computer system needs to perform various tasks. Over the years, CPUs have become faster and more efficient, allowing us to perform complex computations and run advanced applications. But as the demand for more processing power continues to grow, we need new and innovative ways to process data. This is where neural processing units come in. NPUs are specialized microprocessors designed to perform complex mathematical operations required for deep learning and artificial intelligence applications. Unlike traditional CPUs, which are optimized for general-purpose computing, NPUs are optimized for specific tasks such as matrix multiplication and convolutional operation. They can process vast amounts of data in parallel, making them ideal for deep learning applications. In this video, we will explore the architecture and capabilities of neural processing units and how they are transforming the world of AI and deep learning. So sit back, relax, and let's dive into the fascinating world of NPUs. Microprocessors and CPUs have been the backbone of computing for decades. CPUs are designed to handle a wide range of tasks from simple calculation to complex computations. CPUs are excellent for handling sequential operations, but as the scale of data grows, it becomes increasingly challenging to complete computational efficiently. However, as the demand of deep learning models continue to grow, GPUs are beginning to show their limitations. Neural processing units or NPUs are designed to address these limitations. NPUs are highly specialized chips optimized for deep learning tasks. Unlike CPUs and GPUs, which are general-purpose processors, NPUs are built specifically for parallelizable nature of deep learning algorithms. There are two main stages of deep learning: training and inference. Training is the process of creating a model by iteratively adjusting the model's parameters until it produces the desired output. This is a highly compute-intensive process that includes implementation of existing datasets and iterating over it. It adjusts the weight and balance in order to make the model more accurate. Inference, on the other hand, is the process of using trained model to make predictions on new data. For example, when you enter a new piece of data, let it be a camera shot or a sound recording, it processes the input on an already trained model and produces the results accordingly. Training a deep learning model requires significantly more computational power than inference. This is where NPUs really shine, as they are specifically designed to handle the intense computational demands of deep learning training. For chips capable of performing both, these two phases are still generally performed independently. We are not going to go deep into how ML works, because the concept is so vast and beyond the scope of this video. But a lot of machine learning relies on same mathematical functions, that are convolutions and accumulations. They may look complicated, but what they are is fancy multiplication and addition. You need a dedicated processor for this because of the amount of operations. Good part about this calculation is that not all calculations are independent on each other. This allows calculation to be parallelized, which in turn allows plenty of cores to work with and opens massive throughputs to process data as quickly as possible. As we have seen, the onboard machine learning capabilities of NPU enable mobile devices to perform a wide range of tasks with great efficiency. Speech detection is one of the most widely used applications of NPU. It allows devices to understand voice commands, transcribe speech in real time, and perform other voice-related tasks. Another major application of NPU is adaptive battery management, with machine learning algorithms constantly monitoring usage patterns and optimizing power usage for the devices to last longer on a single charge. But perhaps the most exciting application of NPU is in computational photography. With a NPU, mobile devices can perform complex image processing tasks such as real-time object detection, facial recognition, and depth sensing. This allows for features like portrait mode, which blurs the background while keeping the subject in focus, and night mode, which captures bright and clear images even in low light conditions. Computational photography is a field of photography that involves using software algorithms to enhance or manipulate digital images. With the advancement of technology, Mobile devices like Google Pixel and iPhones have incorporated computational photography techniques to enhance their camera capability. One key feature of computational photography is HDR. HDR imaging captures multiple images at different exposure levels and merges them together to produce a single image with a wider range of colors and brightness levels. This feature is available in both Pixels and iPhones. Another feature available in both is the ability to take portrait mode photos. This mode uses machine learning algorithms to identify the subject in focus and blurs out the background, giving the photo a professional look and a shallow depth of field effect. In addition to these features, phones also have night sight, a mode that uses machine learning to enhance low light photos. Night sight uses a combination of image stacking and noise reduction to produce bright, detailed photos in low light conditions. iPhones, on the other hand, have introduced Deep Fusion, a feature that uses machine learning to enhance detail and texture in photos. Deep Fusion captures multiple images at different exposures and uses neural networks to analyze and combine them into a final image with enhanced details and textures. Moving on, as much as I want to explain the neural engine in Apple's new RISC architecture chip, Apple, being Apple, keeps most of its information hidden and details of the technology used proprietary and far from public access. So let's understand the Google's take on NPU with tensor processing units. Google shares their information in this case because information sharing takes place both sides, willingly or unwillingly. Now disclaimer, the case study that we will be discussing is not a consumer-facing chip for mobile devices. This is a server-grade product that is being used in Google's data center. As machine learning has taken off in the last few years, the increased demand for specialized computing resources for training and prediction has led to the development of tensor processing units. But where do they come from and how do they work on inside? We will look at the original TPU, its design, and how it came to be used in everything from Google Photos to Google Translate. The trouble with modern computing is that we keep wanting more power. Unfortunately, we are beginning to run into the very limits of physics. At least this is very true for general purpose processors, which if you want might find in your everyday laptop or smartphone. The need for more specific computational power is what led to the first tensor processing unit to be created. Understanding the original designs of the TPU and why it was built that way can help us as we look forward towards designing machine learning architecture and software systems in the future. The first tensor processing unit was built as a PCI Express expansion card, and it was plugged straight into the existing server racks in Google data center. It had a 700 MHz clock speed and had 40 watts of power consumption. And it's been in production since 2015, powering things like search, translate, photos. Not only was the TPU version 1 much more performant than existing CPUs and GPUs of the time, it importantly had a much higher performance per watt of energy. These two effects combined to make the first TPU a very effective chip. The chip featured an architecture that was specifically for deep learning algorithms. It utilized reduced precision, a matrix processing, and minimal design to reduce overhead. Let's look at each of these now in turn. Neural networks boil down to a rich set of matrices, multiplication, and addition. The team at Google decided to reduce the precision of the chip using just 8-bit integers rather than the conventional 32-bit floating point numbers, and using a technique called quantization to convert or map 32-bit floating numbers to 8-bit integers. So this allowed significantly more integer multiplier units to be fit into a single chip. So speaking of which, let's talk about the matrix processor. Conventional processing systems read and write the memory very often, sometimes after every single operation. This is because they do general purpose processing. So in order to support many different kinds of processing, the hardware design must necessarily be fairly generic. However, this leads to bottlenecks due to all of those memory accesses back and forth. So what if we could build a special purpose processor that performed a much more limited set of operations but did so more quickly? This is what the TPU tries to do with its matrix processor. It uses what's called a systolic array in order to do a large hardwired matrix calculation without memory access. One analogy I've been using to describe this is that a CPU is like printing out letters one by one, stamping them out. whereas a GPU is printing out a whole line at a time, while a TPU, it's stamping out entire pages at a time. The core of the TPU is a huge systolic array, performing up to 250,000 operations per clock cycle. Most of the chip is dedicated to the matrix multiplication followed by additional operations. Even though the clock speed is a seemingly paltry 700 MHz, it is performing a ton of operations every clock cycle. And one final note about all this is that it is important to remember that in order to achieve this design, the TPU version 1 only did predictions. After the TPU V1 was created, the team applied the lessons they learned to the design of TPU V2. As you can see, it's considerably larger than the first TPU and features 4 chips instead of 1. Additionally, it's got some massive heat sinks. It has 180 teraflops of compute, meaning that it can do 180 trillion floating point operations per second. And it does both training and predictions now. The layout of the TPU V2 is quite interesting. Each board has 4 chips, but each chip has 2 cores. Each core then contains a matrix unit, a vector unit, and a scalar unit, all connected to 8 GB of high bandwidth memory. That means in total each board has 8 cores and a 64 GB of memory. And matrix unit is a 128 by 128 systolic array. What's special about the TPU V2 though is use of new data type called bfloat16. The bfloat16 combines the range of a 32-bit floating point number with just a storage space of 16-bit floating point number. And what does the B in the bfloat16 stands for? Brain, since it comes out from the brains of Google team. Of course, you can't get something for nothing. And what we lose here is precision. The bfloat16 is able to represent far fewer decimal places than a standard 16-bit floating point number. However, the team determined that this was worth the trade-off since neural networks can operate at a reduced precision while retaining sufficiently high accuracy, and using the bfloat16 enabled TPU V2 to fit in much more computational power. Combined with designing an integrated chip and placing it on the board with 3 counterparts, so far 4 chips per board, this TPU V2 achieves much higher performance than the V1. Now for really exciting part, the TPU V2 is arranged into pods. One TPU V2 pod is 64 TPUs. They are all connected together and you can use an entire pod as if it was one machine. And since there are 2 cores per chip, with those 4 chips per board and 64 TPUs per pod, that multiplies out to 512 cores in a TPU pod, totaling up to 11 petaflops of processing power. You can use smaller subdivisions of the pod as well as a quarter pod or a half pod. What's really extraordinary is when you start using TPU pods to train up state-of-the-art models on benchmark datasets. For example, you can train ResNet 50 in 30 not hours but 30 minutes. And that's only a half of the pod in use, just 32 TPUs. And when you look at the training processes used, they are using a batch size of 800 images per batch. Quite amazing. And this part of what allows the training to proceed at such a breakneck pace. Now what they did improve for V3, as you can see, they took the V2 and made it blue. But additionally, of course, these chips use water cooling. This allows it to take up much less space vertically. So TPU V3 pods can then support many more TPUs in it. And a full TPU V3 pod comes in at 8 times faster than V2 and weighs about 100 petaflops of compute power. Okay, so that's a lot of big numbers to swallow in one video. Thank you all for joining me in this video and discovering the lesser known world of NPUs. Before we leave, make sure to like this video and put down a comment what you think about NPUs and rise of AI and machine learning. How will the future of mobile hardware look if the demand for onboard AI keeps growing at this pace? Food for thought. Before you leave, let's look at Microsoft's NPU demonstration presented by their legendary presenter, Panos Panay.
Why is there a guitar on stage? Stevie's probably thinking, why is there a guitar here? Because we're going to play it. So Stevie, here's my ask. We're going to have Bob play the guitar as loud as you can.
I'm going to record
Stevie,
him.
I want you to go show this demo so we can get a sense of it, and I want
Right.
you all just kind of see that impact of the product itself.
I'm recording right now, and voice focus is turned off. Oh, you sound amazing. There you go, buddy. Now I'm going to turn voice focus on,
Okay, keep talking.
and that's pretty amazing. You are
Okay, so right
sounding
now voice
awesome.
focus is on.
Correct.
So in theory, they can't hear the guitar.
Correct. Now I'm going to turn it back on. They can hear the guitar again.
Okay, so now you turn it back off. Don't stop, Bob. I want to test this system.
Perfect. We're good. We're good. Perfect.
You
That's
got
good.
it?
You good?
All right, let's pause.
All right, let's
Okay.
play it back.
So Stevie was just doing, all those features were on. He's on a call, and he turned voice focus on. Let's listen.
All right. I'm recording right now, and voice focus is turned. So this is off, hearing everything. Oh, you sound amazing. There you go, buddy. Now I'm going to turn voice focus on.
Okay, keep talking.
And that's pretty amazing. You are
So right now voice focus is on.
correct.
So in theory, you can't hear the guitar.
Correct. Now I'm going to turn it back on. They can hear the guitar again.
Turn it back off. Okay, don't stop, Bob. We're going to now try something else.
We're good. We're good.
But the algorithm, or ultimately the learning coming off the edge and onto the machine, is eliminating everything else. It's early. Some of you look tired. I got it. Long night maybe, I'm not sure, or an early morning. Here's what we're going to do. Without using your voice, because if that made any sense, it will show up. Make as much noise as you can. Clap, stomp your feet, hit the table. Stevie, you start recording.
We've never done this before.
Yeah,
You're making me nervous. There's a lot of people here. I'm being really honest.
Hey, and
What's
you
the
know
worst
what?
case?
And-
What's the worst
and
case?
We're, and we're
All
4
right.
minutes over, so we
So
can
what's the
just
worst
quit,
case?
you know,
Make
so
some
that-
noise. Go, go, go. No screaming, just clap. No yelling.
Okay, I am now recording.
No yelling, no voice.
With voice focus off, and now I'm going to turn voice focus now. And now voice focus is basically turned on, and there's a shit ton of noise behind me. I'm going to turn voice focus back on, off I mean. And there you go.
It's like that was like the closest to being in a
Okay, that was pretty loud.
I've ever. That was
Let's
pretty
see
bad. Even
Let's
if it
hear
didn't
it.
work, that was pretty cool. I just got to tell you, good job. All right, Stevie, let's see.
Let's hear it. I'm crossing fingers. Okay, I am now recording with voice focus off. Now I'm going to turn voice focus now. And now voice focus is basically turned on.
It worked.
And there's a shit ton of noise behind me. I'm going to turn voice focus back on. Off. And there you go. All right.
All right, very cool, Stevie. It works.